Okay, in this section, we're going to basically finish chapter 3 of the textbook that you've never really had, but it talks about sort of the culminating effects of all of the functions. So we're going to take all the functions we learned last class, the family of functions there, and we're just going to apply a bunch of different techniques. So forewarning, this is a relatively long section because it covers 3 main types of transformations. But I think if you can understand all of the techniques that we're talking about in this section, you'll be in good shape. Should be familiar to you for some of you, and hopefully it will make sense, but we'll kind of hit some with a bunch of examples and make sure it's all pretty clear. So there are 3 types of transformations that we're going to discuss. The first one is probably the most straightforward, and those are translations, okay? So translations occur in 2 different directions. You can translate either vertically or horizontally, and that's just, again, shifting the graph left or right, up or down, all right? So pretty straightforward. And we've done this before. We're just formalizing it now into kind of a theoretical sense. All right. So a vertical translation is written in the form of f of x. So take whatever function, and then you're adding a constant above, we'll call that k when you're moving up, or f of x minus k when the graph moves down. Okay. So you're just taking the constant value and adding it outside of the function, or subtracting it outside of the function. And I think that makes logical sense because I think most of us associate adding with going upwards and subtracting with going downwards. And so I don't think there's any issue with that. So if you have some parabola, f of x is x squared plus 2, then I think that makes sense that that graph of the parabola is going to move up. And if it's minus 2, it goes down, etc. Okay? A horizontal translation graphically and algebraically sort of contradict each other, okay? And it's written here in the form f of x plus k when you're moving, I will call it h rather, not k, because k is the y value. We'll call it x plus h when the graph moves left. And it's f of parentheses x minus h when the graph moves right, okay? So it's sort of may seem counterintuitive because you think of, oh, this is plus h, why are we moving to the left? But if you think about factors, if you factor a quadratic and you have x minus 3, x plus 2, your zeros are x equals 3, which is to the right, and x equals negative 2, which is to the left. So think of it in the sense of factoring. Anytime you have a horizontal or an x effect, like finding factors or translating, it's going to be the opposite sign of what you think happens graphically. But because it's in parentheses, that's the key. So look for everything inside parentheses and think of sort of the opposite movement. And if the value is outside of the parentheses, it's going to sort of be consistent with what we know, all right? So let's do a couple examples and we'll kind of see how this works. All right, now all of these you can either use a table or just graph it on your calculator, but we're going to sort of think about what's going to happen before we actually graph it. According to this, we have a plus 2 that's outside of the basic function. So think of your basic function as x cubed. And if you remember from the last section, that sort of has a, what I sort of called a lazy river sort of look to it. And if you graph your points, it has this sort of general idea, right? So that's your parent function. Well, what the plus 2, of course, will do is move that up 2, and then the minus 4 will move that to the right. Now, you can always graph this on your calculator to confirm this or use a table, but hopefully you're getting to the point where you can just look at the function and know how it's going to go. So take the critical points that you use for the parent function, the x cubed, and draw the new ones accordingly. So I'm going to use just a different color to make it more obvious, but we're going to take the vertex at 0, 0, if you will, move it up 2 and to the right 4, and this is sort of the center there. And the point 1, 1, we're going to move it up to 5, 3, and the point negative 1, negative 1 to 3, 1. Right? Again, we're just taking every point and shifting them up to the 2, so 2 in the y direction, and then right 4 in the x direction. And so then when you graph it, you will have something like that. Okay, and you can see all it is the same shape, it's just literally shifting the axes, right? So up 2 and right 4. So that's what we're going to be doing for this first section. We'll do the same thing with a square root function. Now notice the -1, of course, is outside of the square root, so that suggests a vertical translation, so you're going to go down. But think of the parentheses inside the square root. It's not drawn there for you, but that's sort of implied. So the parentheses are implied to be under the square root, which tells you that it's going to go to the left. Okay, so if you think of your parent function as the square root function, that's going to be starting at the origin and sort of moving up accordingly, right? So you have sort of a general graph like this. Again, you can do this on your calculator or use the table of points, whatever is easier for you. But then you're going to take all of those points and move them down 1 and left 3, right? So you're going to have your beginning point of the square root function starting at -3, -1, okay? And then all the points follow accordingly. So you can take any point you have there, move it down 1, and move it to the left 3, okay? And so when you do that, you'll have something like that. Okay, and you're just going to do a quick sketch, but make sure you have some of the points labeled, right? So give yourself, a table of values and make sure that you've identified them. So in case your graph isn't perfectly easy to read, then I can still see what points you're trying to plot. Okay, and so that's sort of a general idea. All right, and then we'll just kind of end with this case. It's a square root, or not a square root, a rational function. So of course you're going to have asymptotes. So think of where the asymptotes would go. Normally, the asymptote would be on the axes, right? So you think of the axes as vertical and horizontal on the axes there. But now this is going to shift everything, right? So the 4 means you're going to go up 4. And because the x plus 2 is all in the denominator, you can sort of think of that as implied parentheses again. So that's going to shift it to the left. So if your parent function in blue is sort of a graph that looks vaguely like this, it's kind of hard to draw with the points the way they are, but you get the general idea. Everything, including the asymptotes, are going to move. So that asymptote horizontally is going to move up to 4, and the vertical asymptote is going to move to the left 2. Now this gets really confusing to see because you've got 2 graphs there, but if you can sort of take away maybe I'll do that, maybe I'll take away the blue graph, and then you can have what's left being the pink graph, and that's your transformed version, all right? And again, we're just taking all of the points and moving them up 4 and left 2. So if you had a point at 1, 1, it's going to move over to -1, 5. And if your point was at -1, -1, it's going to move to -3, 3. Okay? And then, again, you just sort of try to draw it as best you can so that it doesn't touch the asymptotes. And that's why we have the asymptotes, all right? And so there's your final function. So at the end of the day, all you're really doing is shifting all of the points left, right, up, or down, depending on how the function is written. So that's an idea of it graphically. Just some variations on that are just looking at the function and making sure you know how it's written so you can decide which transformation it is. So looking at this next example, if you just have some random point -3, 8, and you're saying, all right, I'm going to take that function, whatever that function might be, and put a +1 after it, that should tell you that, okay, this is going to go up 1, which means I'm going to change my y variable. So the -3 is unaffected, but the 8 goes up 1 to 9. All right, so that's all you're doing is saying what effect does that function change have on the point. Okay, and so take that same point, since x -3 is in parentheses, that tells you that the graph is going to go to the right So that's going to change your x coordinate, right? So you're not going to change your y this time. The y stays at 8, but the -3 goes 3 to the right, which becomes 0. All right, so that's how you want to think of these, is like, does the change algebraically cause me to move left or right, or does it cause me to move up or down? And since the -7 here is outside the parentheses, it's going to go down. So the x stays the same. You're going to change your y. 8 minus 7 is 1. And just to drive the point home, this is going to move it to the left, which means you're going to change your x coordinate. So -3 moving to the left becomes -9, and the 8 stays the same. So notice in each of these cases, you're only changing one of the parts of the coordinate, right? So just pay attention to where the parentheses are, and it should be pretty straightforward. How would you write a function given a verbal description? So there's your x cubed original function. If you want it to move to the left, that means your function is going to have the 7 in parentheses. So that 7 is going to be in parentheses. And then you just got to make sure that you put the right sign. So if it's moving to the left, think of it as opposite x plus 7. Think of it as a factoring scenario. What would the value be? -7, it's when you write x plus 7. If it's up 3, you're doing it outside, so there's no parentheses necessary. You keep the x cubed as its parent function, and then you add 3 outside of it. So note the difference when you have parentheses, where it moves horizontal, and when you don't have parentheses, it moves vertically. And then just to push these examples further, you have it to the right, so that's going to make x minus 4 cubed, and down 5 is going to make it x cubed minus 5. All right, so just make sure you're familiar with how the examples are written and where the parentheses go. But I think it's pretty straightforward from a horizontal translation and vertical translation standpoint. All right, so that's adding and subtracting. When you start multiplying, then we get sort of a stretch or a compression of the graph. So think of just, you're taking a parabola function and you're holding on to the curved parts and pulling it out and making it a wider parabola, or you're pulling it and it's making it a narrower parabola. Okay, so what you do algebraically there is you're going to multiply that function. And again, parentheses play another role, all right? So when you have a vertical stretch, that means you're going to have it in the form of y equals, or let me write f of x. Let me write it as f of x. You're going to have a number a. Let me write it as, you know what? Let me do it this way. Let me write it as f of x on the outside. I think that might make a little more sense there. All right, so if we just have it, write it as a times f of x. Let's do it that way. That's probably an easier way to write it. So take your function and multiply that function by some number. We'll call that number a, and that is going to make it a vertical effect. And a vertical stretch occurs as long as a is greater than 1, right? So if you think of y equals x squared, that's your typical parabola. If you write that now as y equals, say, 4x squared, that's going to make that vertically stretch. And what you can see on the calculator is if you have y equals, I'm just going to do this as x squared here, and then I'll make this as 4x squared. Let's see if I can graph both of these. And you can see the 4x squared is the more narrow of the two graphs, right? It's going to stretch it vertically. So it's almost like you're taking the top of the parabola and stretching it up. And you can see this on your calculator as well. Okay, so that's the idea visually of what's going on. Okay. A vertical compression is written in the same way. It's still written as a outside times a function. It has the same effect. The problem is with a compression, now your values are going to be between 0 and 1. So think of that same parabola. Instead of being x squared, now we're going to write it as 1/4 x squared, right? And so what that looks like is if I take away, here's your basic parabola, there's your x squared. And now if I make this last one 1/4 of x squared, alpha y equals, we'll make this 1/4. That's going to stretch, or that's going to compress it vertically, which has the same visual effect of saying pushing down on the parabola, and you can see it's kind of wider out there, okay? And so we've kind of widened it out. It's compressing it vertically. It's kind of pushing it down to make the U a little bit wider. All right, so that's the idea between vertical stretches and vertical compressions. And I think that makes some general sense, right? You take whatever function you have and you're multiplying it by a number. If the number is greater than 1, it's being stretched. And if it's less than 1 but still positive, it's going to be compressed. If it's negative, we're going to talk about that next. It's a reflection. But for now, we're just dealing with positive numbers. A horizontal compression, again, because it's horizontal, the parentheses are going to have an effect. And so you're going to write the vertical or the horizontal compression the following way. And we'll use the letter B here just to kind of show you the difference. All right, so think of B on the inside, and that's going to make your horizontal distances the reciprocal of that. All right, so it's a little bit more complicated. You take the letter B, whatever number this is, and then you're going to take the reciprocal, and that's going to compress it horizontally. All right, as long as that value is greater than 1, you're going to have a compression. So it's sort of opposite of what we had before, right? In a vertical stretch, A was greater than 1, it was a vertical stretch. In a horizontal compression, the number is positive. So there's a couple little tricky things there, which is why you've got to really pay attention to where the parentheses are. The horizontal stretch then means you're going to have the same function, so there's going to be some number in the parentheses, but that number is going to be between 0 and 1, okay? It's going to have the same effect, but a stretch is going to have the number be a fraction. All right, so it's sort of counterintuitive, but let's take a look at an example, and I think it will make sense, okay? So here is a function, y equals 1/2 f of 3x. Now, I don't know what function that is, so we've sort of created a sketch for you here, okay? So here's just your typical graph. This isn't anything in particular, but this is just some function that was created, all right? So there's your function. There's no real, I guess it's more of a piecewise function, but it doesn't really matter. The point is we're going to take this blue function and change it by compressing or stretching, okay? And so first, let's just make sure we understand what the y values are, right? Let's just look at the function, and the y values are going to be, now notice that the marks go by 2, so it's sort of, something you got to watch out for. But at -6 is negative, when x is -6, y is -3. When x is -2, y is -3. When x is 0, y is -5. When x is 2, y is -7. And when x is 6, y is 1. All right, so that's just making sure you're reading the graph correctly. All right, let's take the vertical compression or stretch first. So that's going to be the outside number, the 1/2. Since it's vertical, it's of course going to affect the y value. And so take these y values and multiply them by 1/2, right? It's a vertical compression, right, because we're between 0 and 1. And so we're going to basically take this function and sort of squeeze it vertically and make it shorter, okay? So take all of your y values and cut them in half. And if you want to make them decimals here, it's easier for you to see, that's fine, okay? But we're basically taking all of those y values and cutting them in half. All right, before we plot that, though, we want to take a look at the x values, right? Since that's in parentheses, this is going to be a horizontal either stretch or compression. And because the b value is 3, right? In this case, b is 3. That's a value that's greater than 1. It's going to be a horizontal compression by a factor of 1/3. So we're actually going to divide each value of x by 3, and that's sort of a tricky thing there, right? So it's 1 divided by b, whatever that b value is. In this case, it's 3. we're going to take our x values and go 1 over 3. Okay, so negative 6 divided by 3 is negative 2. Negative 2 divided by 3 is negative 2/3. 0 is still 0. Positive 2/3 and positive 2. All right, so that's the idea, and make sure you understand this example. When it's in parentheses, it's horizontal. The number is greater than 1, you're actually going to compress it. All right, and so what you have now are our new coordinates of this graph, and we'll see how it both gets vertically compressed and horizontally compressed at the same time. And so we'll see at the new value x is negative 2, the new y value is negative 1.5. You know what, I'll do this in a different color because why not? Negative 1/2. At negative 2/3, which is, I don't know, somewhere between, you know, it's maybe kind of around there. Negative 3/2 there, we'll go put it there. 0 and negative 5/2. 2/3 and negative 7/2, which is about negative 3.5. So you can see this is sort of annoying to graph, but hopefully you get the general idea. The numbers we give you will be a lot nicer, and then 2 to 1/2. Okay, and so you can see that it's obviously being vertically compressed, right? It's a lot shorter than it was, but it's also smushed in, if that's a word, towards the origin. So it's both moving, kind of being compressed inward, and you're doing it vertically as well. Okay, so all the y values are cut in half, and all the x values are cut by 1/3. And so that's the effect of stretches and compressions. Okay, so how would you describe this? You would say that it is vertically compressed by 1/2, and you would say it's horizontally compressed by the reciprocal of 3, so by 1/3. Okay, so it can get a little tricky because you have a fraction for one and a whole number for the other, and they're both compressions, so it gets a little tricky. But try your best at them, and let me know, of course, if you have any questions. All right, so the one disclaimer I will say is that sometimes when you graph something, that the vertical compression will actually look like a horizontal stretch, and vice versa. Vertical stretches may also look like horizontal compressions. So really looking at the parentheses and the notation really helps. And I'll just do a quick example here on the calculator. If I have the graph of, let's say 4x squared. Oops. Close that. There we go. 4x squared. That's going to be a vertical stretch of the graph of x squared, right? There's a vertical stretch, no problem. But if I now put it as parentheses 2x squared, well, if you distribute the square, you get the same function, 4x squared, and effectively you graph it, looks the same thing, right? The graphs look identical, but technically the first graph is a vertical stretch of 4, and the second one is a horizontal compression of 1/2. So if you could see me squeezing the function together with my hands, you would see that smushing the parabola in is the same as stretching the parabola up. It's sort of an awkward thing to do verbally without showing you, but that's the idea. So if you look at the graph, think of me pushing the sides of this in, as I'm trying to do here. I'm trying to push it in. It's the same as stretching it out this way. So it's sort of a weird thing to try to demonstrate on the calculator, but the point is, a lot of times they look the same. So if you look at the way the function is, the second function has parentheses, so it's a horizontal effect. The first function doesn't have parentheses, so it's a vertical effect. Okay. So that leaves our last one, and this I think will be a little bit more straightforward because we've sort of done this a few times, and those are our reflections. We talked in the last section that all of the values for A and B have to be positive, because if they're negative, now we have reflections. All right? And so when you have a reflection over the x-axis, that means you are, when the y values are opposite, right? So we're going to change the y to a negative y, okay? So if you have a point xy, that becomes the point x negative y. And this should look sort of familiar from what we've done in previous sections. And this is the same graph as negative f of x, right? We're reflecting it over the x-axis, so all the y values become switched. And if you're reflecting it over the y-axis, that means all of the x values are opposite. Okay? And so then if you have some random point xy on a graph, it becomes negative xy, right? This is the same graph of negative x. And you might recall this as like even functions, and we'll use the same function of y equals x squared, right? If you think of it as f of x equals x squared. We'll see that in example 5b in a second, right? If you're reflecting it over the y-axis, it's an even function, it looks the same. All right, and so that's sort of the idea. Hopefully breeds some familiarity from what we've done in the past. Okay, so if we have our example here, we have a square root function. All right, and again, we should know by now that that's going to look something like this. All right, there's our parent function. All right, and if what we're going to do is take f of negative x, that means we're going to reflect it over the y-axis. And so if we're going over the y-axis, all of the x values are going to be reversed. Let's see, something like that. All right, reflected over the y-axis. Pretty straightforward, I hope. And then for the last example here, we have a parabola. Of course, we know what a parabola is. We've spent lots of time with those. So we'll just plot a few of the main points, squaring all of the x values. There's your parent function. Of course, we know what a parabola looks like. And then since we're reflecting it with the negative on the outside of the parentheses, it's a flipping over the x-axis. Okay? And again, where the parentheses are makes a big difference. Okay? And so there's your reflected parabola. Oh, look, think of this as, think of this as negative x squared, right? Oh, look at that, it's opening down, like maximums, like we did all of last chapter. Okay? So those are the general concepts. We have translations left and right, up and down. We have stretches and compressions, and we have reflections. So of course, the culminating thing is that we're going to put them all together. And I have several examples. We'll see how many we get through before the bell rings here. I may have to do a second video just to finish up some of the examples. But the idea is that you always want to do the multiplication part first. So specifically, you want to take care of any reflections first and then do the transformations that follow, okay? Sort of an order of operations idea, okay? And so we'll take a look at that. We've got a few examples that I think will really clarify this. Remember, of course, you can always plug this function in your calculator, use the table of values to help you figure out everything, but hopefully as you get used to this, we'll be asking you to describe the translations that you can do them verbally without any issue, okay? So if we have the transformation here, we have the graph is going to go down 6, right? That's what the negative 6, of course, does. And then the 1 on the inside, think of it as implied parentheses. You can think of these as parentheses if you want. It's going to go to the left 1. And then you have on the outside, you have the 3. So it's not part of the parentheses. That's going to be a vertical stretch. by 3, by a factor of 3. All right? So again, if you take your parent function, your absolute value function, you have your V shape here. All right? So there's your general idea of an absolute value function. Not very well drawn, but you get the idea. And so what we're going to do is we're going to take each individual point, and I'll start with the origin because that's the most obvious one. I'm going to move that down 6, then left 1, and plot that there. And then when you stretch it, you're going to take every other value and kind of multiply it, right? So all the y values are going to be multiplied. So from there, we're going to stretch it. Instead of going up 1 over 1, we're going to go up 3 over 1. Up 3 to the left 1, and keep going. Think of it almost like a slope, right? Up 3 over 1, up 3 to the left 1. And that gives you your vertical stretch view, right? And again, all of the original points then are moving down 6 and left 1, but then they're being stretched accordingly. All right, so it's a little bit tricky. So start with that kind of vertex point, and I think from there, everything else will follow. And of course, you can always graph it on your calculator and plot the points. Okay, but that's the general idea. Okay, for the second example, we're taking our parent function, our cubed function, and we're going to do a couple things to it. Right, so the negative here tells us we're going to reflect the function over the y-axis. Right, the x is being made negative. So all the x's are switched. And then the 2, of course, means we're going to go down 2. All right, so if we plot the parent function, all right, something like that. Get the general idea there. When we apply the transformations, then we're going to reflect it over the y-axis and move it down 2. So this point at the origin doesn't get reflected over there. It stays there, so it just goes down 2. And then instead of the y value being reflected 1 value over, it's going to actually, it's going to be shifted, right? So you're going to reflect it down 1, and then it's going to, let me say that again. It's going to be reflected down to -1. Right, you're going to take that point and reflect it down to -1, and then you're going to shift it down 2. You're going to take this point here, reflect it over the axis, and you're going to have the value there. I guess technically it's reflected over the y-axis. And so what we have here, we're going to reflect it over the y-axis and move it down 2. We're going to reflect this over the y-axis and move it down 2. All right, so it's a little tricky, which is why you have your calculator there, but the transformations are in effect. So let me kind of clear this out, and let me, maybe zooming in will be a little bit easier here. So we have our point that we just moved down to, right? Here's our starting point. Then we're going to take this point here, reflect it over the y-axis, and shift it down 2. All right? So there's that point. Let me erase that now and do the next one. Then we're going to take the other point that was here, reflect it over the y-axis, and move it down 2, which puts it here. Notice visually, it looks like a reflection over the x and y-axis look the same, but you're actually reflecting it over the y-axis first and then moving the graphs down. And then if you plot the points or connect the points, you have something like that. Okay, so that's the idea behind it. It gets a little tricky, but again, those table of values will always help you. Okay, let's try a little bit trickier one because now we have a number inside the parentheses that's going to throw things off a little bit. All right, so let's take a look. First thing we know for sure is that we have a reflection, right? So that reflection is going to make it over the x-axis. So we'll talk about that. Reflect over the x-axis. Okay. And now I'm going to do the vertical translation. I know that's going to go up 3, but it gets a little tricky over here. The numbers suggest it would move to the right 2, right? Because you see a -2. But does it really move to the right 2? What role does the 2 in front of the x play? And that gets a little tricky. And if you graph this on your calculator, you'll see that it actually doesn't move to the right 2. And here's why. When you have a number in front of the x in parentheses here, you want to do a little mathematical trick, and that is to factor what's inside the parentheses. So try to get that parentheses, or that x, to be alone, and if you take out a 2, you basically have this. So notice what I did here. I sort of took what was inside the parentheses and factored out the leading term. Now, even if this wasn't easy to factor, you still want to do it because the goal is to try to get this x piece by itself. So if you factor out a 2, that's going to justify why the graph actually moves to the right 1. And again, if you graph this on your calculator, you'll see that the critical point only moves over 1. Right? Because this is on the surface, the parent function is just a simple parabola. Right? So if you graph the parabola, you'll see that the points start off here, but then when you graph the translation, this vertex at 0, 0 only goes to 1, 3, not 2, 3. And that's because of that x minus 1 being left over when you factor out a 2. So that 2 tells us it's going to be a horizontal compression. So it was in parentheses, so it's going to be horizontal. The number is greater than 1, so it's a compression. And that factor is going to be by 1/2. So we're going to squeeze this parabola in to be more narrow, okay? And so when you do that and plot your points, you're going to have a point that brings you to here. All right, again, if you go to your calculator and plot points, you'll see that this is a narrower version of the parent function. Not by much, but it is more narrow. It's like squeezed in by a function of 1/2. So it's about 1/2 as wide as it was before. Okay, so that's a little tricky bit. It's right 1 and a horizontal compression by 1/2, and that's what makes it look the way it does. So that's a little tricky, so just be mindful when you have a coefficient that's in front of the x that you've got to sort of factor it out, okay? And so we'll finally do this last example here, and then I think we'll see where we're at. The rest of it actually isn't too bad, so it'll go a lot quicker. Now, the trick here is that you have a 2 minus x under the square root. So again, before we do any kind of graphing, the parent function is simply the square root of x. All right, so we got that. And we can graph the square root of x relatively easily. Okay. Now we've got a couple things going on. We have the negative on the outside, so we know we're going to reflect over x, so that's not a problem. And we have the +2, which means the graph is going to go up 2. Okay. So when you graph this, you might think, oh, I'm just going to reflect over x, and I see a 2 with a minus, and I might say, oh, that's going to go left or right 2, depending on how you see it. But the subtle thing here is that you have a negative x in well, not in parentheses, but under the radical. So you can think of this function as negative square root of negative x plus 2 plus 2. Right? So the 2 minus x is the same thing as negative x plus 2, right? Algebraically, all you're doing is moving the variable in front and the constant behind. So you might think based on that we're going to move it to the left 2. But you'll see when we graph it that that's not the case. And that's because of that negative x. Just like we factored a 2 in the last example, we want to technically factor a negative 1 outside. And if you factor out a negative, you'll see that we actually are going to move the graph to the right. All right? And so that this origin point is actually going to go up to right 2, and the square root function is going to go starting from there. The negative on the inside here tells you that you're going to reflect over the y-axis as well. So we're actually reflecting this graph twice. Once over the x-axis because of the outside negative, and once over the y for the inside negative. And so when we plot this, you're going to have a point that looks like this. Okay? So we have a graph that looks like that. Okay? So those are your values. Again, it's reflected over the x-axis and the y-axis, but your starting point is up 2 and to the right 2. If this is confusing, and I imagine it probably will be, I can't stress enough to use your calculator and plot the points. That will help you graph these far more easily than just sort of looking at a function going with the points. Go to your graph, use your table to plot the points. All right? Definitely use your table of values and plot them. And that will make, I think, everything make a little bit more sense. Okay? So, according to my clock, we don't have a ton of time left, but let me see if I can just do a little bit more. Maybe I can do one final example, and I will stop this video and finish up next time. Okay? So, let's take a look at some variations on this. And so we'll start with some segment. There's a function that's defined, and it has 2 endpoints at 4, -1, and 2, 6. We'll start with some basic ones just to kind of clear our head a little bit. And we have x minus 3. Of course, that tells me that it's going to go to the right 3 units. Okay? So what does that mean for x? I'm going to change my x value to 7. And I'm going to change my x value from 2 here to 5. Right? That's all we're doing. Taking the original points and moving them right 3. Just kind of like what we did earlier in this lesson. Okay? Same thing here. F of x plus 3 on the outside means it's going to go up 3. So I'm going to take my y values and add 3. So 4, -1 becomes 2. And 2, the 6 becomes 9. Okay? Good. Now we will combine them. So now we have x plus 1 minus 1. So again, that's going to the left 1 and then down 1. So we're actually going to affect both x and y at this point, right? So the 4 goes to the left 1, so that's going to make that 3. And the -1 is going to go down 1 to make that -2. So both things occur simultaneously. 2, 6 moves to the left, making that 1. And 6 goes down 1 to 5. Okay? So now we're going to do both of them at the same time. So you really have to pay attention to whether the function is dealing with an x translation on the parentheses or a y translation outside the parentheses. All right, next example. Notice in this case that there's a reflection over x. You're going to vertically stretch by 3, and you're going down 2. Okay, now it doesn't say to write them all down, but this is what's going on. So if you take your 4, -1 point, you're going to take, Well, in fact, the x value doesn't change at all, right? Because reflecting over the x changes the y value. Stretching it vertically changes the y value. And moving it down 2 changes the y value. So the only effects on any of these are y value effects. So the 4 is going to stay the same. Okay? So what's going to happen is you're going to take the reflection of negative x, so that 4, -1 sort of becomes 4, 1. And then you're going to vertically stretch it by 3, so the 1 becomes the 3. And then you're going to go down 2, subtracting 2 gives you 1. All right, so mathematically, what did we do? We took the -1, our y value, we multiplied it by a -1, and then we multiplied it by a 3, and then we subtracted 2, right? So that's the process that we use. Started with -1, multiplied by -1 to make it +1, multiplied it by 3 to make it +3, and subtracted 2 to make it 1. So let's try that with the other point. We have 2, 6. We're going to take our 6, we're going to multiply that by -1, making it -6. We're going to multiply that by 3, making it -18, and then we're going to subtract 2 to make it -20. Got all that? Hope so, because there's a lot of things going on here, all right? So first thing, recognize that you have an x value, and then we're going to take all of the vertical effects by that. Reflecting over x just switches the y to a negative, stretching it multiplies it, and subtracting it because it's going down, okay? So I'm going to pause here, and then I will pick up the rest of the examples in the next video, but hopefully this gives you at least a start for what we're doing. But if it's a little confusing, and I wouldn't be surprised if it is, please make sure you ask in class. All right, so try your luck and let me know how it goes.